For this project, our group carried out the structural analysis and design of a reinforced concrete gazebo located at UTHM Pago campus. Reinforced concrete was chosen because it is widely used in construction due to its strength, durability and ability to withstand various loading conditions. The project involves site measurement, structural modelling, load analysis and design verification. To complete the analysis, we use several software including AutoCAD, Revit, Microsoft Excel and Esteem. All calculation and design checks were carried out according to Eurocode 2 to ensure that the structure meet the required safety and serviceability requirement.
These projects involve the measurement, modelling, analysis and design of existing reinforced concrete gazebo at UTHM Pago campus. The structure consists of three main elements, which is slab, beam, column. These components work together to transfer loads safely from the roofs or slab down to the foundation. Therefore, this structure is suitable for studying how load transfer occurs in real reinforced concrete structure. For this project, we use several software, which is AutoCAD, Revit, Microsoft Excel and Esteem. So, the design calculation based on Eurocode, which is the standard used for reinforced concrete design. The structure load follow. Load are first carried by slab, then transferred to beam, followed by column and finally to the foundation.
The structure selected for this project is reinforced concrete gazebo located at UTHM Pago campus. This gazebo was chosen because of its simple beam column slab configuration, which allow us to clearly understand the load transfer mechanism from the roof slab down to the foundation. During the site visit, measurements were taken for all structural components, including the slab, beams and columns. Based on our visual inspection, no major structural defects such as crack, excessive deflection or damage were observed. Therefore, the gazebo was considered suitable for structural analysis and design evaluation.
For this part, we compared the actual site measurement with the original SAMDABI. After conducting field measurement, we found that the actual structure dimension are slightly smaller than those shown in the original drawing. So for the slab dimension, the measured slab size was 3.63 meter times 3.55 meter, while the SAMDABI 4.10 times 4.40 meter. So for the beam dimension, the measured beam length was 2.325 meter, the original SAMDABI 3.06 meter. The measured column height was 2.68 meter compared to 2.73 in the SAMDABI measurement. From this result, we can clearly see that the actual structure occupied a smaller footprint than originally designed.
So this is our workflow process using four main software tools. First, we use AutoCAD to draw our 2D engineering plans. Second, we use Revit to turn those plans into a 3D model of the structure. And third, we use Esteem to run the structural analysis and calculate the forces. And finally, we use Excel for manual calculation and double checking with the Eurocode 2 standards. Now for the drawing. First, we use AutoCAD to draw the 2D plan, so we have the exact measurements. On the left is floor plan. It shows the top view, the size of the area and where the columns are placed. In the middle is the side view. This shows how tall the columns and the angle of the roof slope. On the right is the front view. This ensures all the frames align properly from the front. Next, for the 3D drawing, we use Revit to turn our 2D drawings into a 3D model. This 3D view makes it very easy for us to see the full structure clearly and check for any mistakes before we go through the manual calculation.
This slide show how load are transferred through the structure. First, slab receive both dead loads and imposed load. Dead load includes self-weight of the structure, while imposed load refer to the occupancy or service loads. Next, the slab transfer this load to the supporting beams. The beams then collect and distribute the load to the columns. After that, the column carry the accumulated load vertically downward to as axial forces. Finally, the load are transferred from the column to the foundation and then safely distributed to the ground. This load part is important because it helps engineers understand how forces travel through the structures and ensure that every structural element is designed safely.
Next, I will explain about the analysis of structure. A structure system is an assembly of interconnected structure members that is designed to transfer structural load from the structure to its foundation. Some examples of common structure members are slab, beam and column. Structure systems are effective depending on their capacity to withstand loads without compromising their structural activity over their service life. Next, I will explain about the analysis of structure beam. For the analysis of structure beam, we comparison between two data. The first one is manual site measurement and the second one is from the software Esteem. For the effective span length for the manual side measurement, we get around 2335 mm, and for the STM, the length is 3000 mm. Next, for the design action, for both of manual side measurement and STM, the design action value is the same, which is 6.4 kN per meter. And for the measure force, for the manual side measurement, we get around 7.60 kN, and for the STM is 9.81 kN. Next is the bending moment. For the bending moment, value for manual side measurement is 4.42 kN per meter, and for the STM is 7.36 kN per meter. And lastly is the required reinforcement for the steel bar. For the manual side measurement, the required steel bar that we assume is use the 2H10, which is value 157 mm square. And for the STM is we required to use 2H12, which is the value is 226 mm square. And lastly, a 650 is a 675 mm increase in span under the exact same load nearby double the bending moment. That is requiring thicker H12 tension bar to prevent failures.
So next, for the analysis of fracture for slab, we compared the manual side measurement and STM design. So the effective spans for manual side measurement, LX we got a 3.55 meter and LY 3.63 meter. For the STM, LX we got a 4.1 meter and LY is 4.4 meter. Both structure have a same design action, which is 10.16 kN per meter square, and maximum short span moment for manual side measurement is 8.16 kN per meter and STM 12.64 kN per meter. For the design shear force for manual side measurement is 18.36 kN per meter and the STM 20.9 kN per meter. For required rebar for manual side measurement is H8 to 300 4.168 meter and STM H10 to 300. So both configuration pass with regard to serviceability, limit stakes for deflection and cracking, but the large blueprint footprint demands a heavier reinforcement grade, which is H10.
This slide shows structure analysis of the column. We compare the manual side measurement with the SIGN-DABI blueprint data. The results show that columns are classified as non-standard column with standard ratio of 35.3 and 33.1, meaning additional second order effects are not critical. The most significant difference is the actual design force, where the manual side model gives 19 kN while the blueprint model gives 25 kN. The difference occurs because the actual on-site span are smaller, so less dead load and lift load are transferred from the beam to the column. Overall, both column designs satisfy the Eurocode 2 requirement and remain structural safe.
Next, I will explain about the comparison between site measurement data and site drawing. Measurements were taken on site during using measuring tape and compared against the original standard blueprint. Minor discrepancy were observed across all structure elements. For the first one is slab. The measure length for the manual site measuring is 3550 mm. Meanwhile, for the standard drawing, the actual length LS is 4100 mm. Next, for the width LY of the slab. For the manual side, the actual length is 3630 mm. For the standard is 4500 mm. Meanwhile, for the thickness is same 150 mm for the both manual side measurement and standard measurement. Next, for the beam, effective length span for the manual side measurement is 2325 mm. Meanwhile, for standard drawing is 3000 mm. Second, for the width of the beam. For the width of beam for the manual side measurement is 75 mm. Meanwhile, for the standard drawing is 150 mm. And lastly is height. Height for the beam for the manual side measurement is 120 mm. Meanwhile, for the standard beam is 150 mm. Third is column. For the measure size of base time height for the manual side measurement is 175 times 135. Meanwhile, for the standard is 117 times 117. Second is column height. For the manual side measurement, actual height is 2680 mm, but for the standard drawing is 2713 mm. Okay, next, I will explain about the comparison between manual versus standard design result. Both data sets were analyzed under the same design action. WD equals to 6.54 kN per meter for beams and N equal to 10.16 kN per meter square for slab. The largest standard span will produce higher tensile force that require more reinforcement. For the first one is for the slab. For the per meter short span moment, kN per meter, for the manual side, by calculation is we get 8.16 km per meter, but for the standard B is 12.64 km per meter. Next, for the design shear V, for the manual side, the design shear is 18.36 km per meter, but for the standard B is 20.90 km per meter. And lastly is for the main rebar. For the main rebar, on the manual side measurement is we use H8 300, which is 166 mm square per meter, but for the standard B is H10 300, 245 mm square per meter. Next, for the mixture that we get on the based on manual side measurement is 7.60 kilonewton, but based on the standard B drawing is we get 9.18 kilonewton. Next, for the max moment that we get based on the manual side measurement is 4.42 kilonewton meter, but based on the standard B is 7.36 kilonewton meter. And lastly is for the main rebar. Based on the manual side, main rebar that required is 2H10, which is 166 mm square, but for the based on the standard B drawing, main rebar that required is 2H12, which is 226 mm square. And lastly is for the column, actual force and ED that we get on the manual side is 19 kilonewton, but based on the standard B drawing, actual force and ED that we required is 35 kilonewton. And lastly is the tendency ratio. For the manual side is slenderness ratio value is 35.3, but for the standard B is 33.1.
During this project, our crew encountered several challenges. The first challenge was the absence of the original drawings during the early stage of the project. As a result, we had to conduct site measurements manually before obtaining the SAMDABI drawings. Minor differences were later found between the measured dimension and the original drawings. The second challenge involved limitation in manual measurement. Some structural elements were difficult to access, especially at higher locations, and certain reinforced concrete details such as reinforcement size and spacing could not be directly observed. The third challenge was the learning curve associated with the STEAM software. Since most team members had limited experience with the software, additional time was required to learn the analysis procedure and interpret the result correctly. To overcome these challenges, we carefully verified site measurement, compared them with available drawings, refer to the design standard, and improve our software skill through practice and guidance from lecturers.
Reason of measurement different. First, the actual span measured on site are slightly shorter than the blueprint dimension, resulting in a lower load transfer and reducing the tributary area. Second, small error may occur during manual measurement due to limited access and the using of measuring tape. Third, difference between the as-built structure and the original design can occur because of construction tolerance and site adjustment, which can cause the final structure to differ slightly from the original design document for the measurement. Lastly, the reinforcement detail could not be directly verified because they are embedded inside the concrete. Therefore, the bar size and spacing had to be assumed based on engineering adjustment and standard practice using Eurocode 2. From an engineering perspective, Eurocode 2 requires accurate measurement, material property and loading information to ensure safety and serviceability of the structure. Despite the difference, both models meet Eurocode 2 requirement. All structural elements passed the necessary check and the conservative SAMDABI as STEAM value were adopted for the final design to ensure safety. In conclusion, the measurement differences are minor and do not affect the structural safety of the gazebo. To conclude, this project successfully demonstrated the practical appliance of structural analysis and design principle on a real reinforced concrete gazebo structure. We analyzed and designed the beam, slab and column using both manual site measurement and the original SAMDABI blueprint data to accordance with Eurocode 2 requirement. Firstly, all structural elements passed the design check. Both database satisfied the ultimate limit state and serviceability limit state requirement, including deflection, cracking and shear check. Secondly, the SAMDABI and STEAM result were adopted as the final design value. These values are more conservative and provide a higher factor of safety against possible measurement inquiries. Finally, the project provided a very practical learning experience. It improved our understanding of structural behavior, enhanced our skill using engineering software such as AutoCAD, Revit, and STEAM, and highlighted the importance of accurate field measurement in engineering design. Overall, the project successfully achieved its objective while ensuring structural safety, serviceability, and compliance with engineering standards. Thank you.